two of these p-n junctions in series, then I can make a transistor out of it. And that is a device in which you can switch whether it is conducting or not conducting by means of applying a voltage at what is called a gate over here. And so the gate shifts the potential at the end material in this case, and you have a switchable device which can either transmit or not transmit electrons. And that is the heart of all computers which we have these days. So transistors are what needs to be built in order that you have anything which is a microelectronic device. And then I told you that these days the whole setup over here is on the order of 7 nanometers by 7 nanometers in size. This is a very old standard transistor, 25 years old transistor. These days they are 7 by 7 nanometers in size, and we realize 7 nanometers, that's on the order of 30 atoms. So 30 atoms by 30 atoms. That's the size on the surface area of the chip that each transistor has, which is being manufactured. The amazing thing about it is you have the chip, which is that thumbnail in size, and there's not a single mistake on that chip. If there were a single mistake on the chip, it would work. So it is having manufacturing precision to that standard. And people, of course, realize that you need to have a lot of chemistry knowledge these days. When they make them big like this, they swirl thousands of atoms in there. You could just use, in a way, machining of material with a normal lithography of material. But these days, people realize one has to really look at the chemistry of the materials and employ chemical processes in order to get that precision. And so it has become, over the past decade or so, much more a job market for chemists than it used to be in the past for physicists. So it's lots of job market for you. And it's well paying jobs. It is 6-figure starting salaries. So for the next 20 minutes or so, I'll make a very quick tour through how those microchips are being made, that you have a little bit of an idea of where there are opportunities to work. And then we talk about, it's not chapter 15, but chapter 1 here. Okay, starts all out with a piece of silicon. The piece of silicon is a wafer, and in order to make the wafer, which is a round thing, actually these days they are about this diameter, the wafer. In order to make the wafer, you first need an ingot, which you then can slice into your wafers. And in order to get the ingot, you need to pull it out of the mat, because your ingot of silicon here is one single crystal. There might be a few crystallographic effects in it, but it's one single crystal. Just like diamonds, you might have this single crystal. So you start out by having a big molten vat, looks like this, except those were old style machines where the ingot was this big, now the ingot is this big. So the machines are bigger of molten silicon. And you dip a very small piece of the silicon crystal into it, spin it, and then pull it slowly up. With some cooling along the way, very slow cooling. And it takes maybe 3-4 months to pull it slowly up, and you get ingot. Now it's a really complicated process because you look at purities of materials. The dopant concentrations which we were talking about are on the order of 10 to the minus 6. So you need to have 6 nines purity in order to have controlled doping. Really, you need to have 8 or 9 nines purity in the silicon. And so that you have a well-defined dopant concentration there. Which gives some problems, because it means now that all the surfaces of your crucible over here, they must not leach out any of the elements in that. You must make sure that there's no oxygen or other elements coming through the gas phase. It is a really complicated process. And you want to have a constant dopant concentration in your ingot. which, however, when the melt solidifies, silicon preferentially solidifies on silicon because that's a good match, and the boron or phosphorus or arsenic so doesn't like it. So you need to have a much higher concentration of arsenic or whatever the dopant is in the melt than you get in the solid. So you constantly need to change, put extra arsenic and less extra silicon into the melt to balance things. So it's a really complicated process to do, and it takes many, many months. So it's also fairly expensive. Next job, and of course there's lots of chemistry involved in making these melts. The next job would be to dice this thing into wafers. The unfortunate thing is that if you use a normal saw to just dice it, you're losing about half the material. Just because the saw blade is so thick, and you can otherwise make it so thick. So there's efforts in the chemistry of dicing, of cutting, in making thinner cuts with wires, partially electrochemically biasing wires, setting up the right system that you can get very fine kind of wires cutting through the ingot over time in a chemically reactive slurry. And then finally you get your wafers. You need to polish them as the next step. And after you polish the wafer, then you start what really in the semiconductor companies, in the fabs, is going on. So up to what I was talking about now, it was specialized companies which do this kind of work. Now it would be shipped to, say, Intel as a company. And when the people make the wafer, they will probably also have put some oxide on top of that. So what you see over here is a piece of that wafer, and on top of that there is some oxide. Now the oxide might have come on there just by exposure to air. Silicon oxidizes relatively quickly. It might have also come there at a controlled thickness by you heating the wafer in an oxygen or steam, water steam environment, and oxidizing it a little bit thicker than the normal oxide would come from there, and you have an oxide. These days there are also many more complicated ways. These slides are very confusing. So you have an oxide, and now lithography starts. So if you think about lithography in the classical way, what semiconductor companies do to make chips is called lithography. It starts out in step 0, you have or you make a layer, and then step 1, you put photoresist onto that. Meaning you spin coat a polymer blend onto this one here, and the polymer blend is so that when you put a mask or reticle over it and expose it with light, the polymer will change its property. Typically it is so that the polymer becomes soluble where you expose it. In the very old days, you polymerize the polymer and it becomes insoluble through the polymerization, the photopolymerization step. But that has much less resolution than doing it actually the other way around, having photoactivated acid in the polymer and having it depolymerize that way. So that is really what is being used these days. Okay, so you expose it now with light. And as a consequence, you make a pattern into the polymer, and you can develop, you can wash it away, and you are getting the structure in the polymer. The challenge is that we want to make structures which are way smaller than the wavelengths of light. So if you were to go to UCR's clean room, you would have UV lamps over there to do that, and you can get to just barely less than a micrometer in size. But of course, if we want to have something 7 nanometer in light, we need much shorter wavelengths. And this is a chart from some time back, again, where you can see what wavelengths of light people are using. That is in the deep UV. So specialized laser setups are made in order to generate those lines, those light sources here, and you get very short wavelengths, very deep, very high energy photons. And the reason for that is that the wavelengths of the light approximately determines how fine a pattern you can generate with it or can see with it. And so you need to go to somewhere near, not quite 7 nanometers, but somewhere near 7 nanometers in your light in order to see. What you can also see is here that there's a constant trend of going to shorter and shorter wavelengths, which means that all the time the chemistry needs to adjust so that the photochemistry here still works at that wavelength. So there's lots and lots of effort for organic chemists in finding out the better and better polymers and the better and better acids which they can be embedded there in order to make things, in order to make features come to life. There is an alternative to that, and that is not using light but using electron beams to write these things. And that is good for prototyping, and that is one of the things Michelle is doing actually for her PhD work here all the time in UCR's clean room, writing structures with an electron beam, but it is not really used very much in production because it's so meteorite as opposed to exposed all at the same time to the mass. Okay, so now you have your pattern in the photoresist. The way you are shaping your chip, your wafer then, is that through the holes in the photoresist, you can etch. There are many different ways you can etch. You can etch by dunking an etching solution like KOH, but you can also etch in the gas phase. It's much more common to etch in the gas phase, meaning you are creating reactive species in the gas phase, typically by activating them with plasma, just the same thing as in these light bulbs, you have plasma, which you see in all the rooms. So, you have plasma that activates it, that etches it, and you can actuate silicon like that. Silicon is etched gray a bit. So now you have patterned my silicon dioxide here, the oxide, silicon dioxide. People refer to silicon dioxide as oxide. Oxide always means silicon dioxide. So, as the oxide, you etch the oxide down over here. And then, as a last step, part of the graphic step, you remove your resistor. So, this was one lithographic step. You put the silicon dioxide layer on top, you put resist on top, you expose the resist through reticle or mask, you develop it, and then you etch away the material where you had the holes in the resist. One lithographic step. If you make a device like you have it in your iPhone or in your computer, it's about 20 to 30 lithographic steps you have there. So you repeat now. You put a new layer. In this case, people deposit silicon, and they deposit silicon in an amorphous way here. Not making a nice crystal of silicon, but making a jumble of atoms of silicon there. And if you have a jumble of silicon atoms, which you call polycrystalline silicon or polysilicon for short, then it becomes a really very metallic. So this is actually metal now. And the way to do that is chemical vapor deposition, CVD, which is a process where in the gas phase, often at reduced pressure, you start out from reacting species. In the case of silicon, it might be silane, the methane analog to silicon. One silicon atom is 4 hydrogen atoms in the gas phase. And you put that, expose your substrate with that, you heat the substrate, and the heated substrate, the silane will decompose and form. So very frequently you do it plasma-based, where you create a plasma over here, the gas phase, where electrons are separated from molecules, not all electrons, but maybe 1 or 2 per molecule. And as a consequence, you can activate one braking in the gas phase very easily. So you can activate then already one of the hydrogen falls off the silane. And so once it comes on the surface, it is more reactive and you will have a quicker growth on the surface. That kind of CDP over here works in this kind of rough work, making thick layers of jumbled atoms. There can be lots and lots of work done on making better CDP than that. And a great part of the work in my group, for instance, is making better CDP processes for new semiconductor materials. If you were to look at a plasma, it would just look like that. So really just glowing gas where some atoms are free, some electrons are free from the atoms. Okay, you have the deposit layer. You come again with your photoresist on top of it. You expose your photoresist to the mask. You develop it, getting rid of it over here, and then you etch and take it away. So finally, you strip the photoresist. Second lithographic step. So now you have shaped the position where you had your silicon, polysilicon. Next thing is, you might want to change the doping property of the silicon underneath. You put some dopant, maybe some boron gas you expose the surface to, and you heat it up very high so that the boron will diffuse, and you can change that. It's not a very common process anymore, they're better processes. One of those better processes these days is that you actually grow individual layers, just one atomic layer of a semiconductor or an instrument. And that is called atomic layer deposition. The idea in atomic layer deposition is, if I want, for instance, to deposit an aluminum oxide layer, I start out with a surface which has OH group, hydroxyl groups on the surface. I come with an aluminum metal organic aluminum compound, which is in a gas phase, which I evaporate. When that comes on the surface, one of the methyl groups over here exchanges with the hydrogen from the hydroxyl, and the aluminum sticks to the surface, still having methyl groups exposed, one or two on top of it. And this process will end if the whole surface is covered with this methyl aluminum species. Then you have exactly one layer. Now, in the next step, you expose the whole thing to water vapor, and the water vapor replaces the methyl as methane, coming as OH groups to the aluminum. And then you have again a surface which has those OH groups, so you can start over. Each time you cycle, having either the aluminum precursor or the water in here, you only grow exactly one layer of the material. So you can have layer by layer by layer by layer growth. That was first developed for aluminum, and lots and lots of metal organic chemistry over the past 15 years or so has gone into making precursors for pretty much anything that you want to grow on the surface. So you want to have a platinum layer, you can now buy platinum precursors which work in this way. You want to grow the strontium titanium oxide, you now know what precursors you need for that. That has been developed. What hasn't been developed yet, where lots of people are interested in, is making the precursors not only so that you can grow exactly one layer, or two layer, or three layer, or four layer in those cycles, but making them grow only at one spot of that surface. Wouldn't it be neat if they only started to grow here on the silicon and not on the silicon dioxide? And you can cycle and cycle and cycle, and they will never start growing over here. They will only start growing over there. Called area selective atomic layer deposition. Big research field at the moment. Lots of millions and millions of dollars go into that field, developing the organic reactors, metal organic reactors. Lots of opportunities for chemists to have jobs. Okay, and then it keeps going on and keeps going on, and you make more and more of those steps. I'm not going through any one of these steps anymore over here. At some point you will probably deposit some metal in order to wire the whole thing up. That is actually also something where my research group works on, figuring out not using a metal like aluminum or copper or platinum or so in there, but whether we can use metal carbogenides as that metal. Because at 7 nanometer, that wire diameter copper doesn't work anymore very well. And we think we know something which can work well. And so that is part of again what my research will do. Ultimately, you're creating something where here at the very bottom you make the devices. Here is what we just showed you what you did. And then on top of that, you need to put the wires to wire everything up. All the devices. You have now quite literally 1 billion devices on your thumbnail size chip, or maybe pinky nail chip. They're small. And now you need to wire them all up in the right way. And you have maybe 10 layers of wires which go each layer one there, and the next one goes this way, and the next one goes this way again, and you need to wire it all in some way. And you need to keep it flat so that you don't have problems in there. Okay, so there's lots of effort going into it as well. And finally, in your chips, they are 130 nanometer, that was 15 years ago. And it's 90, still 10 years ago. So we are now much bigger. It's a 7 nanometer. You can see all those different layers of wires on top, and then only at the very bottom here, there would be the devices which we were talking about. Okay. So, are there any questions? Yes?
When you say that the reaction happens only in a single layer, how is it that you're figuring out that the reaction stops at once?
Atomic layer deposition here. The reaction stops. It stops because if you're here, you only expose metal groups on the surface. The tetramethyl aluminum will not react with that, or trimethyl aluminum, or whatever you come with. Trimethyl will not react with the methyl groups. It will only interact with the hydroxide group. But they are now all covered. So there's nothing for the trimethyl aluminum to react with. Then you take all the trimethyl aluminum out of your reactor, and then you put water in. And the water can only react displacing the metal. Otherwise, it would just evaporate. So then you make a new layer of more H groups. Does it make sense?
Yes.
How you get only one layer defined that way? Then always get A, B, A, B, A, B, A. Or your way is now A, B, C, D, A, B, C, D if you have more complicated reactors. Depending on how complex the material is that you're growing. Okay, are there any other questions about anywhere in electrochemistry where we did so? Because otherwise we'll be gone. Okay, so from chapter 15 in the book to chapter 1 in the book. Kinetic theory of gases. I have a question for you. We all know that there's air in this room, right? So, and we all know that obviously then there's air pressure in this room. Maybe every second one of you, pick one of those bottle caps and then pass it on. Only every other of you. So while you do that, kinetic theory, let me talk a little bit and then I'll get back to the bottle caps. We can think about thermodynamics. In thermodynamics, we say we have a system, and that system is characterized by a temperature, and that system might be characterized by pressure, or chemical potential, or all of those intensive properties. But really, the system consists of atoms or molecules, correct? And those atoms or molecules, they don't know so much what is the temperature or what is the pressure over here. The atoms really only know I have a certain mass and I have a certain velocity. So arguably the atom knows what is the momentum and its kinetic energy. because you can calculate the momentum and the kinetic energy from its mass and from the velocity. Can you move it then over to the other side? The bottle cap? Okay. So somehow, from that knowledge of the atoms or the molecules, that I'm so fast and I have this mass, people can determine a temperature and people can determine a pressure. But the atoms or the molecules of the gas in this room know nothing about temperature, they know nothing about pressure. They only know how fast they are and how much they weigh. Okay. And so people started figuring out what they call kinetic theory of gases, and for that they defined an ideal gas, which is one which you learned probably in elementary school, maybe middle school. The gas consists of molecules which always move ceaselessly around. The size of the molecules is really small. They don't really take much space up themselves. It's all empty area where they are running through. And if they hit each other, it's completely elastic collisions. All energy stays kinetic energy. It can just be redistributed between particles. Okay, so I think now the bottle caps are probably around. Every other person has a bottle cap. So I would like you to know from you how much pressure we have really in this room. That is why I passed those bottle caps around. So if those people who have the bottle cap, just put it flat on their hand with the flat side in the bottom and the rough side kind of in the top. And the person next to them, please push on that bottle cap with as much pressure as you think the air pressure is exerting in this room on your partner's hand anyway. Think about how hard you need to press on that bottle cap, only on that bottle cap, only on that bottle cap. How hard do you think air pressure is pushing on that bottle cap down? Don't hurt each other, please. But how hard do you think it is? Think about it. Think a moment. How hard do you need to press? Is it a lot of pressure you're getting on that hand? Is it little pressure? Think about it. What do those atoms and molecules in this room give you? Okay, you all got an idea how hard you think you need to press? Anybody still confused? You all think you need to? Okay, did you press as hard as it would have been if you had one bottle sticking upside down like this on there? Did you press this hard? About this hard? No? Did you press about as hard as if there were two bottles stacked on top of each other, like this, on that? Did you press that hard? You pressed harder? Did you press as much as 3 bottles? So how hard did you press? Did you press as if there were 4 bottles stacked on top of that bottle cap? You should have pressed as hard as if there were 6 bottles stacked on that. So all the way up, don't have enough hands to do that. And then 3 more for that. That hard you should have pressed. That is air pressure. We have, you all know it in some way, you know 15 pounds per square inch. The bottle cap which I passed around is pretty precisely 1 square inch in surface area. So 15 pounds are resting on that bottle cap. That is the air pressure in this room. It's quite a lot, isn't it? So the motion of the atoms or the motion of the molecules in the air, and air consists of 99% of molecules and 1% of carbon atoms, somehow impacts the pressure on all parts of us, in all directions, of course, which corresponds to that on each square inch there are these 6 water bottles resting. That's a lot, isn't it? It's an astonishing amount. We don't feel the air so much when we move our hands, so we can feel it a little bit, but not very much. But there is a lot of air and there is a lot of pressure. How much do you think the air in this room weighs? Like 1 water bottle? Like 6 water bottles? It's about as much as a car. So the air in this room is about a ton in mass. So 1,000 kilograms, 2,000 pounds. That's the mass of the air in this room. So there is a lot of air, and it does a lot of pressure. And so it's important to understand what gases do. Even though we don't see them most of the time, we sometimes smell them, but most of the time not. They are still there, and they have a tremendous importance in anything and everything we do in chemistry. And astonishingly, we need only very fundamental mass in order to understand what is going on over here. So, if I have something set up like this, and if I have something set up like this, and if I were to ask myself over here on the right-hand side, on this wall of this box over here, how much pressure would I have on that? Then I can, probably in the 5 minutes or so we have left, or 10 minutes we have left, figure that out. So the pressure, P, which I have on the wall on the right-hand side of this box over here, that is, of course, the force which all the molecules or the atoms in that box exert on that wall, divided by the area. Pressure is always force divided by area, which is the length of that box in y direction times the length of the box in x direction, correct? Divided by length in x direction by length in y direction, that gives me the area x, y, x times y is here, the area of the box in that direction. Everybody fine with that? Okay, now this force over here is the number of molecules or atoms I have in my box times the average force each of them applies divided by Lx and Ly. Fine with that as well? Where this brackets over here, the pointy brackets over here are meaning average. Now the force, what is force? You all probably remember the Newton is a unit of force. How was Newton defined that is the force I need to use in order to accelerate a mass of 1 kilogram by 1 meter per second within 1 second. Kilogram meter over second squared. So it has to do with changing the velocity of something. It is really the change of the momentum, and I'm sorry, it's another P. It's the change of the momentum. Small p here is a momentum, capital P is a pressure, per time that it is elapsed. And still X and Ly. Now what kind of change of momentum do I really have? The change of momentum I have is that this particle here bounces against the wall and is reflected, correct? So if I'm thinking about the momentum, then the momentum I have is that it has 2 times the velocity it had in the z direction. Just the z component of the velocity is bouncing against here, everything else. So 2 times the velocity in the z direction times the mass. And 2 times because first it needs to stop to 0, and then because it's elastic, it needs to move at the same speed back to the other side. So the change of the momentum from going that momentum forward to that momentum backward is 2 times the momentum. I have 2 times the absolute value. So it is 2 times the change, the momentum, change in velocity, 2 times velocity in z direction times the mass. And the time, how much time, what's the time, how often does it happen? Now once the molecule was going against this wall, it needs to go all the way back over here, and then come back over here in order to have that happen again. So the time is the length of my box in z direction divided by the velocity I have in z direction. And I need to think about 2 times the length in z direction because it's 1 time after the bounce needs to go here and back again. So 2 times the length. 2 times the length. Okay, and the whole thing was still divided by Lx and Ly. Would the velocity cancel out? Let me do the math. So I have n over here. This one here, the length in the z direction. The length in the z direction is not a property of the molecule. It's a property of the box. So in that average, I can pull it out of the average. So I can pull it out in the bottom. And then I have Lx times Ly times Lz down here. The 2's cancel. And then I have a Vz, velocity in z direction, divided by 1 over Vz. So this Vz actually goes into the numerator. So I have my average of Vz squared. I still have the mass. Let me put it here. And I have nothing we need to divide it by. Took care of that. Does it make sense? Okay, good. So what I have over here, nvz squared, you know what that is, correct? I mean, we can easily write that in terms of kinetic energy. So this one here, we have n times. So rather than writing here mvz squared, I can write 2 over 2, which I cancelled here, shouldn't have cancelled. So I have a 1/2 mvz squared, and then I have a 2 in front of it. 2 is just a number, I can take it out of the average. And then 1/2 mvz squared is the kinetic energy in z direction. And Lx times Ly times Lz, that's the volume of the box. Okay? Everybody fine with that? Everybody fine with how I came from this mvz squared to the kinetic energy, which is 1/2 mvz squared, and then it's just the 2 which I need to pull out. Which I can,
Can you explain again when you introduced the z component?
The Vz,
Or just the z in general? Like, how'd you get that term?
this one here, Lz.
The whole thing in the bracket.
I started here. I said the average change of momentum per change in time. Change in momentum is 2 times the momentum which it goes in the z direction, z meaning against the wall, correct? Because 1 times will be z, it stops at the wall and then goes at the opposite speed in the other. So 2 times Vz squared, Vz. And then the time it takes was the time it needs to go from here all the way to here and come back. It's 2 times Lz divided by the velocity in z direction. That is what I have in the denominator. And then I will get out of this one here 2 times 1/2 mvz squared, which is 2 times the kinetic energy in z direction. Okay? Okay. Now let me show you something which you probably saw already. If I take this v over to the other side, then I have a formula you kind of know. PV equals N. And then I have my 2 still here, and I have E keen in the z direction, the average of that. PV equals something. You know PV equals energy, right? So that obviously also needs to be nRT, gas law. So This n is a number of particles. This n here is the number of moles. So we have a little bit of difference in that one. But otherwise, we have something where the n goes away. And we see that then the RT has to do something with the kinetic energy in z direction. So what I can do on this side here, without doing anything bad, I can say times the Avogadro constant divided by the Avogadro constant, correct? So then I'll find that the n times the Avogadro constant, that is the same thing as the number of molecules. So what I have is then 2 times the average of the kinetic energy in z direction equals the gas constant R divided by the Avogadro constant times the temperature. Or put in different, usually people put this one over there. The average for the kinetic energy in the z direction of my gas particles is 1/2 T, and they put a constant K or KB for Boltzmann in here, with this KB being, with the KB just being the gas constant divided by Avogadro's constant. This one. This is K Boltzmann. And the 2 over here came from there. So now I also learned that the temperature and the average kinetic energy of my particles are closely related to each other as well. I learned that the kinetic and average of the kinetic energy of my particles in z direction is 1/2 times the constant, which is a well-known constant, just a new name for it, times the temperature in Kelvin. Or put in different terms, if I want to know what the temperature of my gas is, then I only need to know what is the average kinetic energy of my particles in the z direction, and I would do divided by KB and multiplied by 2, right? Then I have the temperature. The temperature is nothing else than a measure for the average kinetic energy of the particles here. So we learned the pressure is just something about bouncing against walls. The pressure is how often do they bounce and how hard do they bounce. The how often part was this one here. How often do they bounce against the wall, and the change of the momentum is how hard do those particles bounce against you. And the temperature is the average kinetic energy associated with the same motion with which they bounce against you. So just from those very fundamental properties of the gas particles here, the velocity, the momentum, and as a consequence the kinetic energy they have, we can immediately calculate what is the pressure in this room and what is the temperature in this room. And so we don't need to use our thermodynamic properties, temperature and pressure. We can work in a kinetic picture of the gas particles, thinking about them moving with a certain velocity and dividing anything and everything we want to know about our system from those kinetic assumption as opposed to using thermodynamics. So what we're going to do on Monday and Wednesday is look into what else can that show us this assumption here about gases. And then on Friday of next week we have midterm, and then in the following week we are going beyond gases and looking at molecules and then what we can learn from these very simple assumptions we made about molecules and how they behave. And Yeah. Next week, the homework which I'm going to assign on Monday will require you to use a lot of Excel on your computer. Please have a computer with Excel ready for that, because there will be quite some puzzle. Okay.